Hello, everyone, and welcome to this session on accelerating real-time computations for sharper stargazing on giant ground-based telescopes. Let me just remind you that we are available for chat during these sessions. So as questions come up, please use the chat button on the bottom right to submit them. And let me start by acknowledging our colleagues from the various organizations that are working on this project at Observatoire de Paris, at the Research School of Astronomy and Astrophysics from the Australian National University, at the Extreme Computing Research Center from KAUST, and at NVIDIA. So before getting into these real-time computations, let me first give you a few basic concepts about our main application, which is adaptive optics. Adaptive optics is a technique that is used on giant telescopes to compensate in real time for the perturbation arising from atmospheric turbulence on the image quality. It is composed of one or several wavefront sensors that are nothing else than cameras equipped with optical devices that are used to encode the phase information into an intensity. And by interpreting the images from this camera, we can understand how to control the actuators of one or several deformable mirrors to compensate for these perturbations. So there is a central system to this, which is called a real-time controller that is responsible for acquiring data out of the wavefront sensor, interpreting this information, and compute commands to apply to the actuators of this deformable mirror. The typical rate of operation for the adaptive optics system is about 1 kilohertz. So it means that the compute pipeline latency should go beyond 1 millisecond. In fact, it should be a fraction of this 1 millisecond envelope. And most importantly, the time to solution must be extremely stable to ensure stable operation of this closed loop system. We call this jitter, and this jitter should be of the order of tens of microseconds or less. So this real-time controller is basically a very heterogeneous computing system with a functional breakdown that is depicted in this diagram here. On the left, you have the hardware that is on the adaptive optics bench, the sensors and the active elements, and then we transfer data to and from this hardware to compute the optimal shape we should apply to the deformable mirror. And we have several components: the real-time controller, which will be the main topic for the first part of this presentation, and the supervisor on the far right, which will be the topic for the second part of this presentation. The real-time controller is really a system that is based on low latency, low jitter computing. Today, it's mostly linear algebra. And we have these very strong constraints on real time. We usually call this hard real-time controller. And the supervisor is doing some machine learning workloads with less constraints on the real-time aspect, and we usually call this the soft real-time controller, or SRTC. So the state of the art today for our real-time control platform is based on the use of GPUs on both these subsystems. And we do that because the GPUs are good for matrix vector multiplies, because they host this high bandwidth memory. And this is good for the hard real-time part. But they're also good for embarrassingly parallel workloads with the thousands of threads running concurrently. And this is extremely good for the soft real-time part of our pipeline. So today we will go into these details and show you how this works in real time and how we plan to even improve the already exciting performance we are getting out of this system. So let me first concentrate on the hard real-time pipeline. And this is the typical timeline for this pipeline. So you see from top to bottom, the various operations and data transfers that are happening during the AO loop. From the CCD integration time, because we are looking at very faint targets. So the shutter of our camera should remain open for a certain time, typically the millisecond, to the what we call the zero order hold on the deformable mirror. The mirror should remain still during the integration time of the camera. And in between, we transfer data, do some computations, update the state of the system. And this whole process introduces some latency in our pipeline. And our goal here is really to reduce this latency to the minimum. There are some incompressible parts, the integration on the camera, the zero order hold on the deformable mirror. What can be compressed is everything from data transactions to computations on the real-time controller. And our overall time envelope for this is about 250 microseconds. This is an average number for different instruments. Of course, you can have varying requirements, but this is really the, let's say, the baseline number with, again, a few tens of microseconds of jitter peak to valley on this time to solution. So let me show you what we do today with our GPUs. In this case, we use a very particular type of wavefront sensor that is called the pyramid wavefront sensor, creating these 4 images of the pupil of the telescope, each of which containing some information that, when combined, can provide the shape of the wavefront. So what we do here is we acquire 240 by 240 wavefront sensor frame at this frame rate of 1 kilohertz. We process the pixel data, doing some integration, averaging, and a number of things to come up with a vector of measurements that we multiply by a control matrix through a matrix vector multiply to get to the actuator's command. The size of the matrix is typically 25K by 5K. In our pipeline, we have integrated a timer to measure the performance with a high accuracy. So I'm going to show you some benchmark results that have been obtained on the DGX1 server with V100 GPUs. We are only using 4 of these V100 GPUs. And we are running an OS that is a standard requirement for these observatories, and this the CentOS version 8. So here is the profile of a single iteration. In this case, we are emulating data acquisition from the sensor by transferring a frame at a very regular rate. And this is this small box you see here. And 1 millisecond after that, we send another frame. And in between, we should do the computations. We have 2 main processes here. One that is doing pixel processing and that is gathering the results at the end so that it can be sent to the deformable mirror. And we have an additional process that is performing the matrix vector multiply. The matrix vector multiply is distributed over 4 GPUs, while the pixel processing pipeline is running on a single GPU. We are using CUDA graphs to schedule efficiently our jobs. And we use what we call a busy wait strategy to synchronize between pixel data acquisition and the 2 processes that are running to perform this pipeline. So if we zoom in a single iteration, so you see here that the matrix vector multiply is distributed over the 4 GPUs. So after these several small kernels that are doing the pixel processing, we send the measurement vector to the 3 other GPUs, and then we have 4 GPUs performing the matrix vector multiply concurrently. We gather the results, and at this point, the results are ready to be sent to the deformable mirror. We are using CUDA graphs to pre-launch these jobs for the next iteration. So this is what enables the very low jitter we are observing in this pipeline. So if we look at an histogram of the execution of 1 million iterations, you see that the mean time to solution, what we call the pure RTC latency, is of the order of 165 microseconds with a very low jitter, again 23.5 microsecond peak to valley with an RMS of only 2 microseconds. So we are already getting this very nice performance. And here I want to thank Stephen Jones for his contribution to making this approach extremely solid and extremely stable in our pipeline. And we have very good opportunities to even scale up in this very simple approach with the new A100 GPU. And I'm showing here the kind of performance in terms of sustained bandwidth that we are expecting for various instruments. So the one I've just shown you is the Mikado instrument, but we are also contemplating even more complex instruments that we will describe in the next part of this talk. So as I was saying, we want to scale up to more complex adaptive optics system, and one of the most complex AO concept is called tomographic AO. And in fact, it comes in many flavors. What we call multi-conjugate adaptive optics is probably the most challenging. What we are doing here is that we are measuring turbulence across multiple guide stars. So instead of a single wavefront sensor, we use multiple wavefront sensors at the same time. And combining the information from these different wavefront sensors, we are performing a reconstruction of the turbulence in a volume. We are doing tomography, as it is done in other domains such as seismology. And this provides us with information where we are able to control multiple deformable mirrors that are conjugated to various altitudes in the turbulence. So what it does at the end on the scientific instruments is that it allows us to get a wide field of view that is fully compensated from atmospheric turbulence. So this is really a science enabler, because the science return from these tomographic adaptive optics instruments is way larger and way more fundamental than with a single conjugate adaptive optics. And one of our flagship projects is the MAVIS instrument. This is a 3rd generation instrument for the Very Large Telescope in Chile. It is the multi-conjugate AO system is feeding an imager and a spectrograph. And the novelty here is that it's working at visible wavelength. So the challenge here is that we are pushing the limits of the concept of adaptive optics, because scaling up to wide field of view, visible wavelengths adaptive optics means more actuators, faster control system, and very precise calibrations of the whole system. So this is a really challenging project. And on top of this, it's fast track compared to what is done in the community usually. And we have to be on sky with the first slide by 2026. So here, the difference with the previous case I described is the control matrix. This control matrix, we call it the tomographic reconstructor. Again, we are using data from multiple wavefront sensors. And controlling the multiple deformable mirrors come with some complexity. The matrix is very complex, but as you can see here in this wide angle view, it seems very structured. And this structure can be connected to the system parameters. And what we have noticed, an important aspect of this matrix is that it has very low structural dependency with respect to the turbulence parameter. So this apparent structure comes really from the system dimensioning more than the operating conditions. And if we look even closer in a small blocks of this matrix, we can see that it is in fact what we call data sparse. There is a lot of redundancy in the information in this matrix. And we can probably use this feature to reduce the number of flops and at the end reduce the RTC latency to get even better performance. And let me pass on the mic to Hatem now to explain you the exciting algorithms we are developing to cope with this.
All right, thank you, Damien. So as Damien mentioned, these matrices are apparently dense, but in fact, they are data sparse. They have lots of redundancy, and one can really exploit that aspect by compressing each and every tile of that matrix to a certain level that would not sacrifice accuracy. And here we're showing a ranks analysis, looking at the most significant eigenvalues of each of those tiles. And one can clearly observe here that most of the eigenvalues that are captured are less than 150, which is half of the tile size here in this graph of 300. So this is really a clear indication that one can compress those tiles to a certain level that can, at the end, translate in a gain in terms of number of operation. And this is yet another graph or cartoon showing the tile structure of this matrix, control matrix, and shows that it has lots of data sparsity structure that can be exploited. And I'm showing in the next few slides how we are doing this operation, how we're moving from the traditional dense matrix vector multiplication to a matrix vector multiplication that exploits the data sparsity of this control matrix. And to do that, we use a tile low rank approximation. We're going to approximate each of those tiles to a certain level. And once we do that first phase of compression, we then have this structure that needs to be exploited. And the way we do this matrix vector multiplication, we look at those U and V bases that are generated from compressing each of those tiles. And the first thing we do after we compress that matrix, we stack the bases. We take all those V and U bases and we stack them across all those tiles of the control matrix. The stacking is really important here is to give us a contiguous memory, to give us an access to contiguous memory, and so that we can perform the proper matrix operation to do this matrix vector multiplication. So the first phase here is to multiply those V bases by the X vector. And this is how we do it. We basically split the V bases vertically and call a batch matrix vector multiplication to perform that first operation. When we do that first operation, we get an intermediate result. It's not the final result. It's a transient result and this YV matrix. And once we've done that operation, we need to take that YV matrix and shift it or transpose it to this YU matrix that is toward the last operation that we want to do, which will operate on the U basis, as shown here in this cartoon. And again, here, what we do is another batch matrix vector multiplication that involve now the U basis with this intermediate YU matrix. The result of that operation is our final Y, is our final Y vector. This is the vector or the command vector that will be sent to the actuators. So if you look at it, then in this new tile rank matrix vector, it relies on those Kublas batch GEMV operation. And there are two of them, two phases that involve those batches. And this is where we need to optimize this kernel to make sure it runs close to the peak bandwidth of the GPUs. So this is some preliminary results showing the bandwidth achieved across multiple GPU generation and looking at the impact of the tile size. So in this graph, we're showing bandwidth. So the higher, the better. So first of all, one can see how the performance trend increase or how the bandwidth increase from one GPU generation to another one. And also, if you zoom in and look at the impact of the block size, we can see a different bandwidth can be achieved depending on the tile size. In particular, for the 800 GPUs, a tile size of 100 will achieve 1.1 terabyte per second bandwidth. This is a graph showing the jittering, showing how much performance variation one can experience possibly in real time. And one can see that most of the bandwidth achieved scored around 1 tera to 1.1 terabyte per second. So we're really happy by the bandwidth achieved here by this tile rank matrix vector multiplication on 800 GPU. This is showing time to solution, right? So the lower, the better across various GPU generation. And we can see that we are below 200 microseconds when running on a single 800 GPU. This is a graphic showing the scalability on 800, moving from 1 to 800. This is on a DGX system. And we can see that the scalability here is in fact limited. And this can be really explained by the fact that the matrix that we are playing with after compression is actually even smaller, much smaller than the initial matrix. So the matrix is not large enough basically to maintain high occupancy and high bandwidth extraction on each of those GPUs. So we're looking at ways of how we could improve that further, and this is still work in progress.
Thank you, Atem. So let me now describe the second part of our control system, which we call the soft real-time optimizer. Here, what we are trying to do is to optimize the parameters of this real-time controller. So basically, we try to optimize the content of this control matrix that we just described. And we have a typical pipeline that is depicted here. And that is made of three main parts. One that is a pure acquisition part, where we retrieve telemetry data out of the AO system, and we build a covariance matrix of all the measurements that have gone through the system. Then we have the two main parts of this pipeline, which is on one side, what we call the learn pipeline, where the goal here is to identify the relevant parameters to fit in our model for a reconstructor, a tomographic reconstructor. And the second part is the apply pipeline, where we compute this tomographic reconstructor. So let me first concentrate on this first part, the learn pipeline. And this is really a model-driven machine learning, where we compare a model for this covariance matrix with the actual data that we have measured on the bench. And we are fitting this model with state-of-the-art optimization approaches, and in particular the Levenberg-Marquardt algorithm, which allows to cope with nonlinear models and various large-scale multidimensional approach. And so in this state-of-the-art, basically, we are using all the elements of this covariance matrix to fit our model to the data. And this can be because of the same property as mentioned before, because of this data sparsity into these matrices. This could be optimized and we could consider only a subset of the elements of this matrix to speed up this optimization approach. And this is what has been developed at KAUST in collaboration with the Observatoire de Paris and the Australian National University. And this is this new stochastic Levenberg-Marquardt approach, where instead of considering all the elements inside the covariance matrix, we only pick randomly a subset of these elements at each iteration of this optimization process. Again, we take advantage of the data sparsity to do less operations and reach faster convergence in this optimization process. And you can see here the kind of results we are getting on the left in terms of obtained Strel ratio out of the adaptive optics system, depending on the time we take to fit this model of the tomographic reconstructor. So basically, we can stop the optimization process at any time, at any given iteration, sorry. And then we would have a partially converged model that we can use to build a tomographic reconstructor that we feed into the system, and we check the performance of the system with this partially converged reconstructor. So if we do that with the Levenberg-Marquardt approach, the classical one, then you see that it takes a fraction of a second to get to reasonable performance, but the real convergence plateau is beyond 1 second, and the maximum performance is reached after almost 10 seconds. Whereas with the stochastic Levenberg-Marquardt approach, we can reach the highest performance in even a fraction of the first iteration of the Levenberg-Marquardt. And in this case, you see here the inset where with the most optimized stochastic Levenberg-Marquardt approach, it takes about 0.01 seconds to get to the best performance. So this is 100 times faster than what we deem as usable with the Levenberg-Marquardt, and this is even 1,000 times faster than the best performance obtained with the Levenberg-Marquardt. On top of this, so this has been done on 8 A100 GPUs, but this scales very well. So this is displayed on the right. And basically, depending on the budget for the system, would it be a budget in dollars or a budget in power consumption or in space inside the telescope dome, we can adapt the number of GPUs we use and still predict very accurately the performance we will get out of this algorithm. So very powerful approach. Again, leveraging the data sparsity of these covariance matrices. So let me pass on the mic to Hatem for the second part.
Yeah, thank you, Damien. So we're entering now the apply phase, which is part of the soft real time. And as you can see in this pipeline, there are lots of linear algebra operation involved, and we're trying to find ways to accelerate those operations on GPUs. And just going quickly about the history on linear algebra, looking at how LAPAC algorithm are basically doing those matrix operation. Mostly they are based on this fork join paradigm, where you'll have a panel factorization that is typically sequential, followed by a phase called the update of the trailing submatrix in magenta color here. This is where basically the performance is extracted from the underlying hardware. And you go on and on until your whole matrix is, let's say, factorized here. And you have this fork and join happening at each and every step. And it has a cost, obviously, to do that. So what we come up with those tile algorithm going from column major format to tile low rank format on the right, we basically take the matrix, we split it into tiles, and we try now to design an algorithm that will operate on the tile itself. And by moving to from a coarse to a fine grain granularity for the computation, we are able to have this, or we are able to embrace this asynchronous execution. And this is really something that is important because it maintains really hardware busy all the time and remove any synchronization that you may have inherent in your algorithm. And once you have made that, you have split your matrix into small tiles, and then you have kernel operating on those tiles, you have many of those kernel, many of those tasks actually running in parallel, and you need a productive framework to be able to monitor the data dependencies between those tasks and making sure you have a proper scheduling, not only for performance, but also for getting the right accuracy at the end. So we rely on those, on this task-based programming model. Once you taskify your application by splitting your matrix into small tiles, you can then schedule those tasks, and we rely on those runtime systems to do that. And there are many runtime systems out there. Some support distributed memory, some would do standard x86 plus GPUs, some would run only on x86. So we have many of those runtime systems that we would like to experiment. And in particular here, we rely on Parsec runtime system. So once you design your algorithm to operate on a matrix that has tiles, you basically end up having this directed acyclic graph, right? So the graph that you see here, the nodes are tasks, and the arrows that you see between those tasks are the data dependencies, okay? So the way to look at this DAG is the width tells you how much concurrency you can have in your application. The height of the DAG is the critical path, okay? So the ideal DAG is a DAG that is width, that is extremely wide, but its height is very small, okay? So this is typically for a DAG, where you have lots of embarrassingly parallel operation. And the important thing here is that when you look at the ultimate solution of your apply phase, you are providing, basically a comment vector that as input will only need 16-bit, okay? Will only take as input 16-bit data streams. So you could do operation in FP64 or in FP32, but at the end of the day that the input given to those actuators would be in 16-bit. So one could really try to exploit that that information from the beginning in your pipeline, okay? And that's something we try to do here. And we're doing this mostly because when you look at the hardware feature available out there, in particular from NVIDIA GPUs, you have really a nice flexibility in doing those matrix multiplication at different precision, okay? And of course, the lower precision you use, the faster you could run those operations. And by looking at the various options and features available on NVIDIA GPUs for doing this matrix multiplication, which is the most time-consuming kernel in the apply phase that we are talking about. So we can see that there is a huge performance possible that can be achieved, and here we're showing the various combination for A, B, and C depending on the precision of those operand. So if you go back to the matrix, this is our control matrix. If you go back to that matrix, we can see that again by exploiting the data sparsity, and approximating, not using low rank approximation, but instead here precision, mixed precision, we can really leverage performance further. And in this particular case, we are basically doing single precision FP32-bit for all the tiles located in the diagonal and around the diagonal. And then as we move farther away from the diagonal, we can lose precision and go to half precision. And when we move even farther away, we could even lose further precision, okay? And here we use single and half precision. We're combining within a single factorization 2 precision at a time. And we rely on a runtime system to really capture the tile specificity and the tile precision, and do it at runtime, do the data conversion at runtime. This is the mixed precision Cholesky factorization. This is the pseudocode. And you can see that we have a heuristic in place to tell us for each tile when we should drop precision and perform operation at a lower precision. And this is represented in the blue here with that heuristics. And the green lines here represent when we need to convert from one precision to another back and forth during the factorization. All this is done actually transparently using a parsec runtime system. All right, so we're looking here at the stray ratio as a qualitative indication of the final image, the final output image. And we want to make sure basically that all the approximation schemes that we want to apply, whether it's low rank approximation or mixed precision, that this does not alter the quality of the image at the end. So when we run everything in single precision, we are achieving 80% in terms of stray ratio, and we can see that the apply phase is resilient to precision loss up to a certain level, of course. And we can see that combination involving half precision and single precision still at the end maintain the stray ratio to the proper ratio of 80% here. And this is for the 8-meter telescope. If we look at the 40-meter telescope, we also are able to find that there are a combination involving mixed precision, single and half precision together, that can still maintain the same stray ratio as if you were doing all computation in FP32. And this is the performance here showing the impact of mixed precision Cholesky on the apply phase. So we're showing performance rate, so flops per second on the left, and matrix sizes. Those are matrix sizes typically of those control matrix, and or the matrix of measurement. And so here, the higher the better. Okay, we are looking at 3 generations of GPUs again, from Pascal to Volta to Ampere, and we're looking at the impact of the hardware technology scaling, and as well as the impact of the algorithm, the mixed precision algorithm. And one can see that if you combine the impact, the improvement coming from the hardware and the improvement coming from the algorithm, which is represented here in the blue arrow, when you combine both, you get a good synergism, and which gives you up to a 3x performance improvement on a single A100 GPUs. And this is really an exciting result. Out of a single A100, we are achieving almost 23 teraflop, and this is really important for us to make sure that the soft real time does not lag behind the real time, the hard real time phase. And with that, I'll let Damien conclude.
Yes, thank you, Hatem. So we presented today our work, collaborative work, on both main subsystems inside the real-time controller. We just showed the results on the soft real-time, and we achieved very interesting performance with this new dual precision Cholesky factorization, where there is a very high productivity using these dynamic runtime systems. Some additional performance optimization could probably be obtained with more static schedulers, but this is already well within the specs we have for our instruments. Now, on the hard real-time part, we have presented this new tile low-rank matrix vector multiply approach. We are obtaining extremely promising results so far, but this is still a very simple implementation with a constant rank across the matrix tiles. So this is a best case scenario, and we still have to work on how to balance these computations over varying tile sizes and varying ranks across the matrix. And let me remind you here that matrix vector multiply latency is really a key design parameter for our adaptive optics system. Better performance means maximum science return, but it also means that we have an additional margin in our very tight time envelope. And this means that we will be able, with this margin, to implement even more sophisticated control approaches and increase even further the final performance of our adaptive optics system. And most importantly, as we are moving on with more and more challenging projects, we can confidently target the future generation of extremely large telescopes and merge all the approaches we have presented today and investigate opportunities for mixed precision tile low rank approaches for the hard real-time controller. So we are leaving you with these nice pictures. The landscape in terms of optical telescopes in Europe and in the US, and a cartoon showing the real meaning of what we are doing here and how increasing the performance of the adaptive optics system gives us the opportunity to observe from the ground as if we were above the atmosphere. That's it for today. Thank you.
Thank you very much.